Good morning, everyone. Hopefully you're all doing well on this fine Wednesday. Can you guys hear me okay, by the way? I haven't streamed using Zoom in quite a while, so not from this machine. Thumbs up? Okay, cool. All right. So today we're going to be talking about motor imagery BCIs and CSP. Let me make sure that things are recording. Okay, things are recording. Good. Also, I'm not sure for the people who watch the podcast normally if this is just going to be a black nothingness because I'm not in the class. So anyway, I'll just upload the actual Zoom this time. But yeah, today we'll be talking about motor imagery BCIs and CSP. I did try to condense everything from the lecture I was going to give on Monday and today, and I ended up condensing it a lot. So I may end up going over things too quickly. If so, just, let me know if there are any questions. We'll also talk a little bit more about some of the details of motor imagery BCIs in the future. I'm planning on having a guest speaker, either Mata Musavi, who was a BCI researcher in my lab, or my advisor, Professor Desa, talk more about the future of motor imagery BCIs and CSPs. So that'll probably happen sometime in week 7, week 8 area. So this is really just going to be introductory into how motor imagery BCIs work and how the most popular tool that we use for motor imagery BCIs, common spatial patterns, works. But it's a very rich and developing field, so hopefully we'll hear more about that later from people who are actually doing that research. So let's get a quick conceptual overview of what motor imagery BCIs are all about. So first, the motivation for motor imagery BCIs is very similar to the motivation we have for all of our other BCIs. We're mostly trying to create assistive devices for people who are somewhat unable to interact with the world normally. So this could be people who are quadriplegic or locked in, something like this. And in this case, we would be trying to utilize the fact that we know that there's this change in the brain when somebody imagines movement, rather than something like an event-related potential like we have in the P300 based BCIs. So the control signal is completely different. It is no longer ERP based. Instead, this is something that is related to the actual oscillations that we see on the cortex of the brain. So typically we have subjects imagine specific movements. We'll most often do a 2-class classification, which is a left versus right hand. This is because the left hand and the right hand are lateralized in the brain. And on average, for right-handed people, you're going to see, the brain is configured in this way such that the opposite side of the brain controls the opposite side of the body. So if you're imagining left-hand movement, for example, you would see that change over the right hemisphere of the brain. And if you're imagining right hand imagery, you would see that change over the left hemisphere of the brain on average. We also sometimes have participants do foot versus tongue. This is just because, and I'll show you the human homunculus and the topographical map of sort of what the cortices map in terms of motor senses and connections. But anyway, left versus right is not too hard, and foot versus tongue is not too hard. Using all 4 of them is not uncommon, or even using just 3. So in a paper that we'll talk about, they'll use left versus right, but then they'll also use foot as a way to sort of signal that they've chosen something. It's also not uncommon to utilize a non-signal. So because of the signature of motor imagery, whenever you imagine any type of movement, or you actually start moving, if you're doing real movement, you're going to see this change across all of the relative motor parts of the brain over the motor cortex and somatosensory cortex. So you can actually pretty easily detect if somebody is imagining some movement versus no movement. And you can imagine creating a system where you utilize that as your control signal. So for example, you have the subject think of something new every 2 seconds. And if you're detecting that they're not thinking of anything, you can use that as like, okay, I'm going to now press enter or select this or restart or whatever. And the goal is to determine what somebody is imagining. We can use the signal to control some device. So this could be a robotic arm going left or right. It could be a cursor on a screen moving up or down or left or right. And it could be cycling through a dial, but it could be any number of things, right? So what you map your movements to, up, down, left, right, or, north, south, east, west, whatever you do, it doesn't really matter. You don't even have to necessarily map them to directions. They could be arbitrary, but these are some common use cases. So the heart of motor imagery lies in these oscillations called mu oscillations. And they're named mu because they sort of resemble the Greek character mu, the lowercase mu, just one after the other, sort of following each other in this cascade. And here we've plotted 3 channels. This is channel C3, so CZ is at the very center of the scalp, dead center. To the left of it is C3, and to the right of it is C4. And what we can see is that before somebody starts motor imagery, we see this very high mu oscillation activity, both on C3 and C4. And then as soon as they're cued to begin starting motor imagery, and also when they get into motor imagery, we actually see a decrease in the amplitude of mu. So we can see we have very high mu activity on both these channels. Motor imagery starts, and then we see a decrease in mu in both of the channels. So this is one of the difficulties in motor imagery based BCIs, is that even if you're thinking, okay, I'm going to be, I'm thinking about moving my right hand, okay, we would expect to see that change predominantly on the left hemisphere. So that would be C3. And we do see this attenuation, decrease in amplitude of mu oscillations, but we also see that over the right hemisphere as well. And in fact, you'd see that not only on C3 and C4, but you'd see that across all of the electrodes that are sort of spatially over the motor and somatosensory cortices. Also, sorry if I have to take breaks. I do still have a sore throat. And as always, feel free to ask questions in chat. So the difficulty that we have when we're designing these motor imagery BCIs is to find some way to discriminate between 2 classes, even though we're getting a change in information across multiple channels. So it wouldn't be enough in this case for us to just be like, okay, we're going to look at C3 amplitude, we're going to look at C4 amplitude, and we're going to see which one is lower, and we're going to choose that as our class, for example. That would be increasingly difficult to do, and I'll show you some figures for that. The activity is also not just localized in the mu band, which is essentially it's the same as the alpha band, somewhere between 8 and 12 hertz, maybe 7 and 12 hertz, depending on the individual. We'll also see changes in beta, which is the frequency right after alpha. So it's going to be typically between 12 and 30 hertz. So you will see a difference not only in alpha, but also in beta when people perform motor imagery, or also when they do some sort of voluntary movement, or even if they watch somebody else do a movement. And these oscillations are quite robust, and they're also quite old. And part of the reason why we're able to record them so well is because they're generated right at the cortex. So if you remember this from one of the first lectures, this is the human homunculus. It essentially shows how much distribution we have for every part of the body on the cortex. And again, we have a lot of surface area dedicated to our hands because we're very dexterous creatures. And we also have a lot of a lot of space dedicated to our tongues and our mouths because we speak and we need high dexterity there. And the way that this is organized allows us to sort of have these spatially discrete regions where we expect to see the most change in our different classes. So, for example, when we have subjects imagine left-hand imagery, well, actually, depending on how you're training them, you'll actually have them imagine pretty rich actions, such as, imagine opening a door that you from your childhood home or something, and really like grabbing that doorknob and twisting it and stuff. So that would activate a lot of different parts of the body. That might go all the way from shoulder to thumb, So you'd activate this massive region of the cortex. And again, this is going to be lateralized, so you'd get a slightly different response from left and right hand imagery. And you can see why we would then use something like the tongue and the foot as the other control signals, because spatially they're quite far away from our hand and arm areas. So you'd have much more temporal lobe activity from the tongue and the mouth, and you'd have much more central activity from imagining the foot, the toes, the legs, things like this. These signals can be harder to reach because they are deeper into the fold, but people can still typically reliably pick this change up. And the first person to observe these motor imagery oscillations was Hans Berger, who was also the main pioneer of EEG. And he observed that you see this attenuation in the activity when somebody does actual movement. Or I can't remember if he was the one to see it in motor imagery, but he definitely saw it back in the 1930s in people who were about to do a voluntary movement, like voluntarily move their hand or something. And you see that attenuation very early. So I think it's something like 2 seconds before somebody is going to move their finger. You can see this attenuation. So there is this preparation step that the brain takes before enacting some sort of movements. And the specific signal that we see with this decrease in amplitude is known as the event-related desynchronization. So the brain has these oscillatory neural networks. And when I say neural networks, I mean real organic neural networks. And for reasons that are not completely understood, the brain really likes to oscillate around 10 hertz. It's a very common oscillation pattern. We see this with the visual cortex and the resting state alpha, but we also see this in the motor cortex. And before some sort of movement onset or imagined movement, we see this desynchronization in these networks such that which results in the amplitude at the cortex, at least, decreasing. Now, depending on how deep in the brain you look, this event-related desynchronization is also coupled with an event-related synchronization in like the lower parts of the brain towards the thalamus. So it's not like it's just all the brain is completely desynchronizing. It's sort of when we see it at the cortex, we're seeing this ERD, but there's also a corresponding ERS at other parts of the brain sometimes. So the ERD, event-related desynchronization, is a decrease in oscillations. And as the event-related might hint to, it's locked to a specific event. And you can think of this as the oscillatory equivalent of the event-related potentials. And the ERS is sort of the opposite. And it's often studied alongside ERD in alpha, but again, we see ERD and ERS in beta. Just the brain is very much active in this alpha/mu frequency range. So we see a lot of activity and change in activity there. So whenever somebody is gonna, this is sort of just reiterating, but whenever somebody is actually moving, imagining moving, or seeing somebody else move, we'll see a desynchronization in alpha and beta frequencies. We're going to see this over the motor and somatosensory cortices. And we're typically going to have more attenuation over the contralateral side, which is opposite side, as opposed to the ipsilateral side, which is the same side. And this is dependent on handedness. So for your dominant hand, you're going to see a larger contralateral ERD and less ERD ipsilaterally. But if you're imagining your non-dominant hand, the ERD is going to be mostly contralateral, or you're going to see a little change in both. So it sort of depends. Everybody's brain is different. There's also this phenomenon called BCI literacy or illiteracy, in which some people just struggle to have control signal or signals that are viable to be used as control signals within BCIs. So not everybody can do motor imagery well. This is not a very widely understood phenomenon, although a lot of people are studying it. There seems to be some correlation between high alpha power in general and BCI literacy in general. So if you can record very nice high power resting state alpha over the occipital cortex, then that subject has something like a 60% chance or greater of being a good BCI subject. And if you can't see that high resting state alpha, then they have a much lower chance of being a good BCI subject. This could just be due to the fact that because alpha is so prominent, if you can record that, then the person has a cortex such that the folds are generous enough for you to be able to pick up these signals. But again, everybody's brain is different. The folding of the brain is different for every individual. So not everyone is going to be equally able to do these types of BCIs. And this is actually a non-trivial problem. So you'll see this in patients who are locked in or completely locked in. They'll have some embedded system like a microelectrode array or something over or within the motor or somatosensory cortex. And the goal that these researchers have is to use that signal in order to, control some speller device or some BCI using motor imagery. But instead, they have to, they try and they realize, okay, dang, this person's motor imagery doesn't work. So now let's try to see what else we can record in this location to still make a usable BCI. So sometimes you do have to be adaptable, and sometimes an individual can use one type of BCI system, but not another type of BCI system. It just really depends on the individual. So let's talk about one of the cooler motor imagery spellers, which is the hexospell. I talked about the P3 version of this when we talked about the P300. This was also developed by Ben Blankertz, and essentially, the actual stimuli were hexagons. So like these circles were hexagons, but I didn't really want to change my original stimulus. And in this case, rather than having the individual circles highlighted, there was an arrow in the center of the screen, and the arrow was rotated with motor imagery. So if you were thinking about right hand imagery, then it would be moving clockwise. And if you were thinking left hand imagery, it'd move counterclockwise. Once a user wanted to select a subset of characters, they would imagine a foot movement and the arrow would stop. And then if the user continued thinking about foot movement, the arrow would grow. And the arrow would grow until it intersected with the region. And once it touches the region, it selects it. And then spelling starts again with the subset of letters. So again, we're choosing our group, and then we're expanding our group over, and then we just do the exact same methods again. So we'd rotate the arrows left to right, and then use foot to select and grow the arrow. So this is an example of using your motor signal and mapping it one-to-one. You're still moving left and right, but you're using it not as a way of controlling something actually moving left or right, but you're using it to move this dial in order to spell. And in a lot of cases, spellers are sort of the first line of defense, I guess I should say, with people who are in a state that need it, because if they can communicate that they need some sort of care, or that they need, maybe they want a channel on the TV changed or something, it might be a lot easier for them to communicate that to a caregiver who can then enact that change, rather than creating some environment that is fully controlled by the user. So that's a much harder design problem and engineering problem. So let's think a little bit about how we would make this BCI. So we'd obviously need to record some training data, because we'd want to make a classifier that can do this automatically. So maybe we'd have a training scenario where we show a participant a stimulus that's either going to be left, right, or foot. And we say, okay, whenever you see the left hand, think about moving your left hand. Whenever you see the right hand, think about moving the right hand. Whenever you see foot, think about moving the foot. And we would have this labeled data so that we can then train a supervised classifier to be able to discriminate between these classes. We would obviously want to bandpass filter the data in order to, extract the data that's only in the frequency bands that we think are going to be useful. So in this case, we know that the bulk of the information we're getting is going to be between the mu and the beta bands. So maybe we'd have a filter from like 7 to 30 hertz. And we can just say everything that's not in there is probably not going to be relevant. Maybe it's just going to be artifacts or just non-signal. So we want to get it out of there. We'd then want to take this filtered signal, send it to the classifier to determine the class. Maybe we just take the Fourier transform, then we look at the power and we say, okay, if the power is higher in this category, then it's probably going to be this class. And then once we've made that decision, we send the instruction to our system. So a pretty generalized set of steps, but let's see how, let's sort of start unraveling this and take a much more complex look at how we would do this and some of the pitfalls of doing it naively. Okay. So there's this one set of figures from the Blenkert's paper. By the way, it's often cited as being from 2007 and 2008. It was actually accepted in 2007, but the magazine was published in 2008. So you'll see it cited both ways. But here we have an example of somebody doing motor imagery. And we can see that the dark line is left hand and the light line is right hand. And in this case, we have activity over CP4. So this is going to be on the right side of the scalp. What's interesting about this is actually the subject's power is higher over the ipsilateral hemisphere. So in this case, when they're thinking of right hand imagery, we actually see a higher power as compared to left hand imagery over the right hemisphere, which is sort of the opposite of what you would expect in the normal case. I just wanted to point that out. This happens sometimes. But as we can see, if we were just going to compute the power of the signal, we would really struggle to separate these two classes. Maybe as individuals, as experimenters, we'd be able to say, okay, this is enough change to say confidently that, okay, they're probably thinking of right-hand imagery, but a classifier is going to struggle with this. And what you'll see at this lower part of the plots, this is going to be the R squared of the signals, which is essentially just the variance of the signals. And I think what they do is they subtract one class from the other, and it's essentially going to be a measure of how discriminable the two classes are. So you can look at this lower plot to get a sense of how discriminable a classifier would be at differentiating these two. So as you can imagine, we can definitely do better than just our raw signal. And in this case, raw/filtered, I think is about the same. Like even if this is just a bandpass filter from 5 to 30 hertz, that's still essentially just raw. One thing that we could do is we could maybe utilize something called a bipolar reference, where we would take our channel of interest and subtract it from some other channel in order to accentuate the differences across two different regions of the brain. So in this case, you take an electrode that is more frontal from the electrode we're interested in, and we subtract the electrode we're interested in from that electrode. And now we can see that we're getting slightly more discriminable information. So this is definitely an improvement. Perhaps a classifier would be able to separate these. Again, we see that our R squared is going up in this region, but this is still not that much information, and it would still be difficult. So we'd want to try to look at some other stuff, but this is not a bad attempt, right? So now we're trying to utilize some way of accentuating the information that we have spatially in order to get a better classification result. We can also compare this to the common average reference. So before I go on to a tangent about that, I just wanted to show you that this also increases discriminability, and we're also starting to see that change across the power spectrum. So if we look at just bipolar, we're seeing some areas where both of our lines are intersecting, but then once we get to common average reference, pretty much starting at 10 hertz, the power spectra are completely separated. So we could imagine that if we're going to take the average power between both of these classes, and then try to use that as a single value to determine which one is higher or lower, that the common average reference would do even better than the bipolar. Now, as an aside, whenever we're recording EEG, we're using some differential instrumentation amplifier. And so all of our voltages at a single location are referenced to some other reference channel. This can be a single electrode, or it could be within an amplifier reference, depends on the system. But we call these electrodes reference electrodes, or just references for short. Sorry about that. So a lot of the reference electrodes we might use would be single mastoid, which is just going to be one of the electrodes on the left or the right, like right behind the ear. We could also use a linked mastoid, which is just going to be essentially treating two mastoid electrodes as if they're one electrode. Or the average mastoids, which is just the average of those two electrodes. One sec, sorry, my throat's really hurting. Historically, you would also see researchers utilize the nose as a reference, although this has sort of fallen out of favor, out of fashion. And in some cheap systems, you'll see the earlobe as a reference, either the left or the right, or sometimes people will use linked earlobes. The choice of reference is going to influence how all of your other signals look. And some signals you can only see with certain references. So for example, there are some lateralized signals that require you to use one of the mastoids versus the average in order to see this hemispheric difference. But in general, people will use references that are widely cited in the literature for the signal that they're looking at. And you shouldn't just decide this at random. The common average reference is becoming a lot more popular. And essentially in this case, you take, like, let's say if you have 64 electrodes, every individual electrode would be, you would subtract 1/63 of every other electrode's signal from that electrode. And that's essentially the common average reference. Simulated references are typically in amplifier references, and these are used for people who don't want to select a reference electrode during recording, but you can always just re-reference offline for free. Essentially, it's a linear operation. And there are also reference-free approaches such as current source density or the surface Laplacian, which is actually one of the methods that Blankert's used. So after the common average reference, they tried the Laplacian, and all the Laplacian is essentially you take your electrode CP4, and what you do is you'd subtract the activity from the electrodes that are its 4 nearest neighbors, or in some cases the 8 nearest neighbors. So I'll zoom that in. So for example, you're going to say, okay, I want 100% of the activity from my electrode of interest, but I'm going to subtract out 1/4 of all of the electrodes that are neighboring it in order to sort of maximize. Think of this as sort of like an edge detection thing. You're trying to maximize the difference between the electrode of interest and its neighbors in order to accentuate this change at this electrode. Typically, so this is one way to naively implement the Laplacian. Typically, we just compute the second derivative. That's how most of the toolboxes work. Oh, I see a question in chat. Does a simulated reference mean they pick one of the electrodes after recording, or they calculate it afterwards? So the simulated reference is typically a reference that's created by the amplifier itself, which would mean that your EEG signals are not referenced to any actual signal. And then what you would do is offline, once you've collected all of the data that you need, you would often choose a reference electrode like the single mastoids or average mastoids or something, and then re-reference your data to that new reference channel, if that makes sense. So you can always re-reference your data because it's a linear calculation. So you can do it whenever you want, and you can always change a reference, no problem. There's no penalty to choosing one reference while you're recording and then switching it afterwards, essentially. I hope that helps. You can read more about referencing in the ERP lab documentation or the EEG lab documentation. They have pretty good blurbs about it. And also Steve Luck's Intro to ERP Technique. That textbook is really good. So yeah, that's a surface Laplacian. And again, we see an improvement over common average referencing. So now we're seeing much more accentuation, especially between 10 and 15 hertz. So this signal is starting to get pretty good. And actually, the surface Laplacian is a very good choice in general. So this is an example of taking this Laplace filter and then examining it over the time series data. And we can see that when the participant is imagining left versus right hand imagery, we can see that the attenuation in left is like quite accentuated in this case, and the attenuation in right is quite accentuated in this case. So you can imagine that a classifier would have pretty much no problem discriminating these two signals from each other. And what we see here are the actual spatial patterns of this activity. So we can see that the Laplacian filter sort of maximizes, and in this case, plus and minus are sort of arbitrary, but with the Laplacian, it's sort of showing that more activity is going towards this region of the brain, on the scalp, I should say, this region of the scalp, and activity is like leaving this region of the scalp. And so we can see these nice spatial filters that are sort of hemispheric. Sometimes they're diagonalized. That's not uncommon. But we're sort of seeing that it's learning this difference between left and right just by accentuating the source information at individual electrodes. But we can do better than that. And one of the best spatial filtering techniques we currently have is common spatial patterns. So we can see here that common spatial patterns sort of blows Laplace out of the water. Not only are we getting this really discriminable information within our alpha or mu range, we're also starting to see much more discriminable information in our beta ranges. So CSP performs really well. It's pretty much only ever used in processing EEG data. I don't think I have ever seen a use case of CSP anywhere else. So it's not an algorithm that any of you will be familiar of from just traditional machine learning courses in the past. And I should emphasize here that CSP is not a classifier, it is a spatial filter. So you can think of it sort of as a supervised dimensionality reduction tool where you have these labeled data sets, you know, which class something belongs to, and you're trying to maximize the variance in one class and minimize it in the other class. So here's a toy example of that. We have this two-dimensional data. In this case, you can pretend that the two dimensions are two different channels, maybe C3 and C4. And you have individual trials or individual data points within a single trial across both of these channels. And you can see that these are somewhat Gaussian plots, and they're centered, they're zero mean data. So they don't difference in means, but we can see that they have slightly different variance. And again, this is not particularly useful because there's a lot of mutual information, right? These signals are correlated, and we can tell because they're not perfectly orthogonal, they're not perpendicular to each other. So what we'd want to do is we'd want to learn some sort of transformation, some sort of set of rotation and scale that maximizes the variance for one class in one dimension and minimizes variance for the other class in that same dimension, and then vice versa for the other dimension. So this is sort of what we would expect as an output of CSP afterwards. So now we have these two signals that are independent from one another now, they're orthogonal. And we can see that, for example, if we look at the blue circle within our x-axis, the variance is minimized, but in the y-axis, it's maximized, and then vice versa for our red channels. So again, this is sort of just like a supervised dimensionality reduction tool, and it allows us to learn these spatial filters that are going to give us the most discriminable information between two different classes. And the way that we do that is through a generalized eigenvalue problem. Now, the math for this is actually very complicated, like the proof itself. There's some Lagrangian analysis, and I am nowhere near good enough at math to do that proof or walk anybody through that proof. So you'll just have to, read the Blankert's paper, for example, the 2007, aka 2008 paper that'll talk about why this works. But there are also proofs for like why generalized eigenvalue problems can be solved in this way. But our goal is to essentially learn this this spatial filter, which is going to be a matrix. In this case, within code, we call it V, which is going to be storing all of the eigenvectors. Okay. And if you've taken any class that has taught PCA, you'll know that the top eigenvector, for example, will show you the most variance in the data set. The second eigenvector will show you the second most variance in the data set, so on and so forth. The only difference between, well, there's a lot of differences, but one of the differences between CSP and PCA is that in this case, the eigenvectors are giving you information relative to a certain class. So in the two class situation, which is sort of what CSP was designed for, the top eigenvector is going to show you the maximum variance for, let's say your left-hand imagery, and the bottom eigenvector, the very last one, is going to give you the highest variance in your other class. So what we end up doing when we compute these eigenvectors is we will choose the top k eigenvectors. Typically, this is 3. So we'll take the 3 highest eigenvectors that are related to maximizing class 1, and we'll take the lowest 3 eigenvectors, which essentially are going to be used to discriminate class 2. And those are our spatial filters. So we'll end up having this, 6-dimensional filters that we will learn and we'll take, and then we'll apply our data through these filters. And that will be the application of common spatial patterns. And so although the math might be quite difficult, the equations don't look that scary, but like getting here is what's scary, and proving it's right is scary. But it's very easy to do this in MATLAB and Python. So a MATLAB, it has a built-in eigenvalue solver. So you do eig covariance of class 1 as one argument, and then covariance of class 1 plus covariance of class 2. And in this case, your actual eigenvectors are going to be stored in the first variable, which is v, and d is just going to be your a diagonalized matrix of your eigenvalues. So you would choose essentially you're assuming that these are going to be sorted, which they should be, but you're going to be choosing the eigenvectors corresponding to the highest and lowest eigenvalues. So they should already be sorted, but if you have some sort of implementation that doesn't sort them, you actually want to index the eigenvectors using your top and bottom eigenvalues. And then within Python, you cannot use NumPy's eig. So if you Google linalg.eig, there's going to be a NumPy version of this. The NumPy one cannot solve generalized eigenvalue problems. You have to use the SciPy version of it. And when you use SciPy's eig, you format it exactly the same way as you would in MATLAB. But in this case, the first return is going to be the eigenvalues, and they're not going to be diagonalized. So it's just going to be the values. If you wanted to turn this lowercase d into the MATLAB uppercase d, you would just multiply it with the identity matrix of the same size. But in both cases, v is going to contain your eigenvectors. Also, as a note, if you take a toy data set or something and you try this in MATLAB and Python, you're not guaranteed to get the same eigenvectors. There are infinite eigenvectors that are just going to be scalar multiples or non-zero scalar multiples of the eigenvector. So even though the values that you're going to see are not going to be the same, the vectors are always going to be some sort of scaled scalar multiple of what you get from MATLAB. So this confused me at first when I was testing to make sure that this equation was correct, because I actually had never done this in Python before. I've always used MATLAB. So I verified this and I was saying, the values are different, but it's okay. They are still the same vectors. They're just not necessarily the same scale. So then once we've computed our v in this case, those are going to be our filters, and we can see that under the filter category, you can see that there's sort of this center surround pattern. So it's emphasizing something within a certain region, and then it's subtracting all of that information out. And again, the polarity doesn't really matter in this case. And we see that both for the left and the right. So we're learning these filters that are sort of maximizing, think of this as sort of just like increasing the slope at certain key channels. But the filters are somewhat, they're very discrete. They're kind of confusing to look at from just a visual analysis perspective. So we'll often plot the actual patterns themselves, which are just the inverse of those filters. So you literally just compute the inverse. And the patterns are much more smooth, and they show this much more gradated hemispheric difference. In this case, this is a bit of a weird pattern, but it's still sort of, it's a more diagonalized. Maybe there is some artifactual information in this, but this still is not uncommon to see in motor imagery patterns. And it's, again, trying to differentiate using spatial information are two different classes. I'm conveniently not talking about how CSP works with more than that, because with like 3 classes, for example, because there are multiple ways to do that. So for groups that are interested in doing CSP and motor imagery stuff, I can send you in that direction, make a Piazza post or something, and I can send you documentation for how that works. But in reality, you're probably going to use a toolbox like MNE, which already has support for a multi-class CSP. And if we actually look at how the time series data looks after we apply it through our spatial patterns, so in this case, the researchers took the top 2 and the bottom 2. So we have CSP-R1, CSP-R2, CSP-L1, and CSP-L2. So these are just the top two eigenvectors and bottom two eigenvectors. We can see that when we apply these spatial filters, we can visually see this difference in the classes. So in this case, when there's right-hand imagery, we see a massive attenuation over the right spatial filtered data. But when we look at the left spatial filter data, we're not seeing any change in variance at all, or even the variance is increasing. And that makes sense if we think about what we're actually trying to do with CSP, right? We're trying to minimize variance in one class, maximize it in the other. And so we can see that temporally here, and we can see that it works bidirectionally in both classes. So in this case, the filters are operating as expected. What we then do is we actually just compute the power over this region, and we would take the log of that. Essentially, when we take the log of that, it makes the signals more Gaussian, which we can then use within a classifier that expects some Gaussian signals, like linear discriminant analysis, for example. So after we've done these filters, again, we just compute the power, we take the log of that, so we get single values out of these dimensions. So in this case, we took the two top filters from left and right, so we have 4 different dimensions. Most of the time it's going to be 6 dimensions. So we have relatively, we've taken this very high, maybe like 64 or 128 dimensional space of our sensors, right? And we've learned filters such that we can automatically reduce the dimensionality to 4 or 6D, which is good because oftentimes with EEG data, we don't have that much data. And the higher dimensionality our data are, the more likely we are to overfit whenever we're doing any sort of machine learning, or we increase the variance whenever we're doing any statistics. So reducing it into a lower dimensional space like this, where the classes are even more discriminable, is really ideal. So as an overview of the standard CSP pipeline, we'd epoch our data around an event. This is going to be the norm. This is assuming we're doing a synchronous BCI, which again means that we know when these events are going to occur. Which is a much easier problem than an asynchronous BCI, which is sort of constantly looking for a control signal. But either way, once we think we have the start of an event, we would epoch, or we're always working with epochs. We would then bandpass filter and zero mean our data. Typically, this is going to be a filter that's going to be between 7 and 30 hertz, but that's not necessarily always going to be true per individual. And the choice of bandpass filter is actually going to have a big effect on the performance of CSP. It is not uncommon nowadays to use a filter bank approach, and actually we're going to explore that in the 4th homework. So you would not only just take this, you wouldn't take this giant filter, but you would actually use multiple different smaller chunks of filters. So for example, something like 7 to 9 hertz and 8 to 10 hertz and 11 to 12, and you would apply, you'd go through and you'd learn these spatial filters for all of these different filter banks. And then you can either use the result of all of those filter banks and both spatial and temporal filters and use those as your dimensions for your classification, or you can use some sort of cross-validation to learn the optimal filter banks. There are a ton of different things you can do to increase your signal extraction when it comes to motor imagery and CSP. You then stitch together these epochs, compute the covariance matrix, compute the CSP filter, and then you would take the top and bottom K eigenvectors. Typically that's 3, but again, you could learn this K through cross-validation. You then run your data through these spatial filters, compute the log power, and then all you'd have to do is train a classifier on these signals. And in this case, LDA would be a good choice for that, since you're going to get these Gaussian signals after you've taken the log power. So this is a general overview of CSP and how you'd use it for motor imagery. Again, there's a lot more that you can do with this. I'd see a quick question on explain what an epoch is. Yeah, so an epoch is going to be a segment of data that is locked to a specific event. So let's say you've told a user to start thinking about left-hand imagery. that's going to be our, let's say that's our time 0, right? The second we tell them start thinking about left-hand imagery, our epoch would then be some window of time. Let's say it's 0 milliseconds. So right when they start imagining it, to like 2 seconds afterwards. And we would extract that data, and that would be one epoch of our data. And we would do that for all of our different events. Okay, so that's all for today. I'll talk more about the project and a little bit more about motor imagery on Friday. And yeah, I'll try to be in person on Friday, but it's going to depend on how well I'm feeling. So I'll keep you posted. But yeah, feel free to ask any questions in Piazza, and I'll have my office hours virtually today. So I'll see you guys virtually then.